So for the last part of this lecture, we will study the effect of affine transformations to the Lebesgue-Borel measure on Rn. And to be precise, what do we mean by this? So let us consider an affine transformation. Say A, a mapping from Rn to Rn, wherein A of x, and we will write this simply as Ax, as the product of some matrix M plus B or plus A, see, okay, where M is an n by n matrix, and A is a vector in Rn. So this is what we call an affine transformation. So it is a translation of a linear transformation. So in particular, if A is the zero vector, you have a linear transformation. So the goal is to relate the following Lebesgue-Borel measures. So the Lebesgue measure of E and the Lebesgue measure of the image of E, where E is a Borel set in Rn. So can we find a relationship between these two Lebesgue measures in terms of the data, which is the given matrix M and the vector A? To have an intuition of what we are heading to, let us consider an example. Let us denote by, let's say, E, the triangle having the vertices 0, 1, 1, 0, and 0, 0. So this will be our set E. Well, this is the set of points in R2 such that X and Y are non-negative and the sum is less than or equal to 1. So the boundaries are included. What if, okay, I take, let's say, the vector A to be the vector for 3. And let us define, let's say, the map PA from R2 to R2. So here we are, let's say, taking M to be the identity matrix first. So T sub A of XY, okay, and we will not, we will write vectors in what? In column form, okay. So T sub A of XY is mapped to, let's say, X plus 4, and then Y plus 3. So that would be a translation. Okay, so with this, let's look at the image of the set E under the map A, T sub A. So what we do is we we compute the image of the vertices. So in this case, let's say T of T sub A of 0, 0 is equal to 4, 3. T sub A of 1, 0. So we need to add 1 on the first component. And finally, for 0, 1, you need to add 1 to the last component of the vector A. So this should be 4, 4. So what are these points? So 4, 3 would be this point, 5, 3, and then 4, 4. So this will be your image. This would be T sub A of E. So this is basically a translation by vector A. So you translate all coordinates or all points of your triangle E by 4 over 3. And you get this triangle. And from this of course, clear that the Lebesgue measure, in this case, it is the area of the image. Of course, the area is 1/2. This is equal to the Lebesgue measure of E. And this is what we call translation invariance. So if you translate a Lebesgue, in this case, the Lebesgue measurable set E under the mapping T sub A, you get the same area. So the Lebesgue measure, at least for this triangle, is invariant or does not change under translation. Okay. Now, for the next example, okay, suppose I have the following mapping. Suppose that we map the vertices in the following way. So the origin is fixed. 1, 0 is mapped to, let's say, 2, 1. And 0, 1 is mapped to, let's say, 1, 2. So in this figure, we have the following vertices. 1. And let us form this triangle here. This should be 2, 1. And let us highlight this new triangle. Then this will be the image under some linear transformation. Now, if I, let's say, let T sub M to be the affine or the linear transformation defined in the following way. So T of M of XY is equal to the following matrix. So the first column would be the image of 1, 0. The second column would be the image of 0, 1, which is 1, 2. Here, M would be this matrix. It is a 2 by 2 matrix. And you can see immediately that this is invertible since the determinant of m is equal to 3. So that would be a 4, 2 times 2, 4, minus 1, so that would be 3. And one can check that indeed this triangle here would be the image of your set or your triangle E. So the image of a triangle under an affine transformation is also a triangle. So if we look at, let's say, the area of this transformation, so the Lebesgue-Borel measure of the transformed triangle PME would be equal to calculate the area, we need to determine, or it is enough to consider the determinant of the matrix formed by these two vectors. So this is the vector 2, or I should say 1, 2. This is the vector 2, 1. So this is 1/2 of the determinant, or the absolute value of the determinant of that matrix, which is basically M. We need to put the absolute value to make sure that this is indeed non-negative. But take note that the area of E is 1/2. So we can write this as the absolute value of the determinant times the area, or that is the Lebesgue-Borel measure of your triangle E. So with respect to a linear transformation, in this case, the effect of the Lebesgue-Borel measure under this transformation M is you have this extra scaling factor. So the scaling factor would be the determinant of the transformation or the determinant of the matrix associated with the linear transformation. So let's say this is the scaling or transformation factor. So here the determinant is 3. So with respect to this matrix M, the area would be 3 times with the previous one. Well, you can check, of course, that the area of this is indeed 3/2, because the area of this triangle here would be 1. The area of this is also 1. And the area of this is 1/2. Since this square here, the area is 4. So to sum, or you take the difference, so 4 minus, this is 2 plus 1/2. So you will get 3/2. So that is 4 minus 1 minus 1 minus 1/2. and that is 3/2. Okay. In fact, this is what is our main theorem in this section. So if we define A from Rn to Rn as follows. So Ax is equal to mx plus A. M is an n by n matrix that is invertible, and A is in Rn. Then the Lebesgue measure or Lebesgue-Borel measure of the image of a Borel set is equal to the absolute value of the determinant of the matrix M times the Lebesgue measure of E. So take note that A here has no effect. As we said, a translation does not change the Lebesgue measure. And this is the goal of the succeeding discussions. And we will prove this in several theorems. So to start, let us establish the translation invariance of the Lebesgue-Borel measure. So let's start with the following theorem. So the Lebesgue-Borel measure on Rn is translation invariant. That is lambda n of E plus x is equal to lambda n of E for any E that is a Borel set and for any x in Rn. Here, the set E plus the vector x is defined to be the set of all y plus x where y is in E. So this is the translate or the translation of your set E by your vector x. So to prove this, let us define the translation map. Let's say tau raised to x. So this is the map defined as follows. So tau x of y is basically y plus x. Y in Rn. Then tau x is, you can check that this is invertible, and the inverse. Okay, let's say in the case of R, n is equal to 1. If x is positive, then this is translation to the right. Then the inverse should be translation to the left. So this is tau to the negative x. And if x is negative, the directions will be reversed. Okay, so also tau x and its inverse tau negative x are continuous. Hence, they are measurable with respect to the Borel sigma algebras, of course. Thus, okay, applying the result on image measures, this is a measure on Rn. So again, this is defined as follows. So lambda n of tau, the inverse of tau raised to negative x is tau x. E, a Borel set in Rn. Okay. So in this case, we can write lambda e plus x as follows. So e plus x is nothing but the image of e under this translation map t to the x. And from here, we know that this is the following image measure. Okay. So therefore, in this case, we need to show that if we want translation invariance, we need to show this. And from this, we have expressed the Lebesgue-Borel measure of the translation in terms of the image measure corresponding to tau raised to negative x. So we need to show that lambda n is equal to, or this image measure corresponding to the translation is the same as the Lebesgue-Borel measure. Okay, by uniqueness, according to the uniqueness theorem, it is enough, okay, since we have a sigma finite measure space, enough to show this for cells, since the cells generate the let's say the Borel sigma algebra. Okay, so for let's say two vectors in Rn with a less than b, let us compute the image measure with respect to this cell. According to this, we have lambda n a b plus x. However, this set is the same as the cell a plus x, b plus x. And if the coordinates are given by subscripts, then the Lebesgue-Borel measure of this translated cell would be the product of the right endpoints. So that would be b sub k plus x sub k. So we're using this now. minus the left endpoint. So that would be a sub k plus x sub k. And you can see that x sub k will cancel, and you end up with the product of the difference of the components or the corresponding components of the vectors a and b. And of course, we know that this is the Lebesgue-Borel measure of this cell. So therefore, we have verified that the two measures, that is this image measure and the Lebesgue-Borel measure, coincides on all cells, since the cells generate the Borel sigma algebra on Rn, and since these measure spaces are sigma finite, this implies that we have this equation, meaning this is true for any Borel sets in Rn. Okay, so going back to the theorem, the Lebesgue-Borel measure is translation invariant. Okay, so what if we have a translation invariant measure on the Borel set? How is it related to the Lebesgue-Borel measure? So let us consider the following theorem. So let's start with a translation invariant measure on the Borel sets. Then one can find a positive constant such that mu, your measure, is a multiple of the Lebesgue-Borel measure. So in other words, a translation invariant measure on the Borel sets in Rn is actually, or is nothing but a multiple of the Lebesgue-Borel measure. Well, in fact, one can compute the constant A by evaluating this at the unit cell. So if we, let's say, note that the Lebesgue measure of this cell, this is equal to 1, since all endpoints are equal to 1. Hence, A would be the measure of this cell as well. So you apply this to both sides of this and apply this equation. Therefore, you get the value B. Okay. So to prove this, let us consider the following cube. Okay. So this is the cell having endpoints that are equal to 1 over m. Here, of course, m is a positive integer. Okay. And let say a to be mu of, so if m is equal to 1, this notation implies that this is q sub 1. So from the above discussion, it is natural to set A to be mu of Q sub 1. Okay, then the following collection, so Q plus S over M. Here S is the following vector having components S1 to Sn, where S sub k is an integer from 0 to m minus 1. So these are the components of your vector S, and k is from, let's say, 1 up to n. Then this collection forms a partition of your unit cube Q1. So to have an idea of this remark here, let's say in the case n equals 2, and let's say m is equal to also equal to 2. So Q1 half would be this part. So we will divide this into 4 parts. This would be Q1 half. And here are the coordinates. So if we take, let's say, S to be 0, 0, that would be Q1 half. This would be Q1 half plus, let's say, 1 half 0. So you translate it by this vector, and this would be Q1 half plus 0, 1 half. And this is, let's say, Q1 half plus this vector 1 half, 1 half. So it is a partition, since take note that this side will not be included in the upper, but will be included on the lower set Q1. Okay, and similarly, this part will not be included on the upper portion. However, it will be included in the lower portion. And similarly, these 2 parts. So in other words, this dash red lines will be only counted once. So indeed, we partitioned this unit cube Q1 into 4 sets. Okay, continuing with the proof. So if you have a partition, therefore, we can apply additivity of your measure. So the measure would be the same as the measure of the union, and hence the measure of the sum of the measures. So here S is taken to be an n tuple, wherein S sub k, or let's say this is an element of, so we have the sum over all tuples S, wherein components of the tuple will be in this set. So this is the Cartesian product of the set 0, 1 up to m minus 1 n times. So this is mu of q 1 over m plus s over m. So copying the sum, and then by applying the translation invariance, of mu, the measure of q1 over m plus s over m is the same as the measure of q1 over m. Since these are now independent with respect to s, so you are taking the sum of this how many times depending on how many, or depending on the cardinality of this Cartesian product. And of course, the cardinality is equal to m to the n. Hence, this will be multiplied by a factor m to the n. Okay, so therefore, mu of q1 is equal to m to the n mu of q1 over n. And let us highlight that one. So here we have partitioned the unit cell into smaller cells having side length 1 over m. And you just need to count how many cells or subcells do you have. So in this case, we have m to the n cells. Okay, so we now consider a cell, let's say QR. So this is the Cartesian product of these cells, r to the n, okay? So first, let us consider the case where this vector r having the components r1 to rn are all rational. Of course, r sub k is positive for k from 1 to n. So from this, we write, okay, so r sub k being a rational number, we can write this as, let's say, p sub k over m. Okay. However, it is possible that the denominators are not the same. However, we can make the rational numbers to have the same denominator by taking m to be the least common multiple of the denominators of r sub k. Okay, so here, since the rational numbers r sub k's are positive, we can choose p sub k and n to be positive integers as well. Then, similar as before, if we form the following collection sub n such that here S is a vector with coordinates S sub k in, okay, now we take the denominators, or I should say the numerators, up to pk minus 1. K is from 1 to n. Then one can check that this is a partition of your cube QR. So again, applying translation invariance. So a similar computation as before. So mu of, let's say, QR would be, so we just need to count the number of tuples satisfying these properties. And you can easily check that there are P1 times P2 up to P sub n tuples in that form by basic counting principle. And you take the measure of Q1 over M. So you just need to take the measure of this set since we know that mu is translation invariant. So here we applied the additivity of mu and its translation invariance. Okay. Take note that here we can calculate the measure of Q1 over M. This is equal to the measure of Q1 divided by M to the N. And before we have set A to be the measure of Q1, so this is A over M to the N. Applying this equation here, so again, this is equal to A over M to the N. So splitting M in the denominator n times A, you have this. However, P1 over M is R1, P2 over M is R2. This should be R1 times R2 up to Rn times A. And take note that this is the Lebesgue measure of QR. So this is lambda n QR. Okay. So therefore, mu is equal to A lambda n. However, for cells starting or with left endpoint 0 and so far a rational Qn. Okay. Now, suppose in general that R is in Rn and R is positive. So in other words, all of its coordinates or components are positive. So we are now considering the case where the right endpoint is not necessarily a rational number. By the density of the rationals, one can find a sequence, let's say R to the K of rational numbers such that R to the K are also positive, and R sub K increases to R. So by this we mean component-wise. And this should be replaced by a subscript. Okay. And therefore, the sequence of cells increases as well to the cell 0R. This is QR, this is QR to the K. Now, if we apply the continuity from below of your Lebesgue measure and your Borel measure mu, take note that a measure is continuous from below. Therefore, we have the following. So mu of QR. This is the same as the limit as k goes to infinity of mu QRK. Again, due to the continuity from below of your measure mu. And we know, take note that RK is now rational. So we can apply the previous case, this one. So replacing R by R to the K. So this is equal to A lambda n QRK. A is constant, so we can pull the limit out. And the limit of the Lebesgue measure of QRK, since QRK tends to Q sub R, then this is equal to Q sub R. Okay, so mu is equal to A lambda n 4 cubes with 0 endpoint. Now, for the general case, in other words, for the case of a cell, one can apply translation invariance once more. So in other words, if let's say I have two vectors in Rn, and A is less than B, then mu of this cell, AB, this is equal to mu of AB plus negative A. So we translate it with respect to negative A. So applying the translation invariance of mu, you have this one. Okay, so here this equality is due to the translation invariance. So performing this sum or this translate is basically the translate. Okay. And this is the cell Q having endpoints corresponding to the components of the vector B minus A. Okay, and we know from this step here that this is equal to A lambda n Q B minus A. And writing back the definition of Q B minus A. And here this is equal to A lambda n we have we need to replace the a, since we have a constant a there, with a different parameter. Let's say c. So this should be c, b minus c, b minus c. And therefore, this must be cb. So not to be confused with this coefficient here. Okay, so again, we have verified that mu is equal to a lambda n for every cell in Rn. And again, by the uniqueness theorem, since these two measures coincide on the cells, and again, the cells generate the Borel sigma algebra. Therefore, we can conclude now that mu is equal to a lambda n. So for our next theorem, let us consider now the effect of the Lebesgue-Borel measure with respect to a linear transformation. So let T sub m be the map given by, so T sub m of x is just the product of an n by n matrix M with a vector x. So that's the action of this linear transformation. Then the Lebesgue measure of the transformed Borel set E is equal to the determinant of M, or the absolute value of the determinant of M, times the Lebesgue-Borel measure of E. And once we have established this, using the fact that the Lebesgue measure is translation invariant, then we end up with our main theorem here. So take note that this is the composition of what? So an affine transformation is basically a composition of a linear transformation and a translation. So here A has no effect, since we already know that the Lebesgue-Borel measure is translation invariant. So for this, for the proof of the main theorem, it is now enough to consider the case where A is equal to 0 due to translation invariance. So this theorem will be proved or established in several steps. But first, let us consider the following annotation. We will denote by m star lambda n. This is the image measure corresponding to the map Tm star. Lambda n. So here, we replace this by m star based on this, based on the definition of your linear transformation T sub m. So in other words, we identify the linear transformation with respect to the matrix corresponding to that transformation. So this is annotation. Take note that this image measure is well defined. This exists since T sub m is continuous hence measurable. Okay, so we need T sub m to be measurable in order for this image measure to be well defined. So for translation invariance, so we would like to establish that this image measure, this would be our first step. So this is translation invariant. So for the proof of this step, so let us take a Borel set E in Rn and X in Rn. We show that. Okay, going back to the previous slides. So to prove a translation invariance, we just need to prove this property here, the one provided in this equation. So translation invariance means that this part here has no effect in the measure. So applying that, we need to show in this case that this image measure is equal to this image measure as well. Okay, so to prove this, let's start with the left-hand side. Applying the definition of the image measure. So this is M inverse lambda n tau of x of E. Okay, since take note that tau inverse x inverse is the same as tau of x, where tau raised to x is the translation operator by x. Okay, so well, we can write this as what? M star lambda n E plus x, and applying the definition again, we have here M inverse of E plus M inverse of x. So here we applied the definition of the inverse or the image measure. And we know that this is, since lambda n is translation invariant, so this is lambda n M inverse of E. However, by definition again, this is the image measure M sub star lambda n. And therefore, from this, we establish the translation invariance of M star lambda n. Okay, now according to the previous theorem, since M star lambda n let's say is translation invariant, I can write this as A lambda n. So again, translation invariant measure on the Borel sets in Rn must be a multiple of the Lebesgue-Borel measure. So for some positive number A. We claim that M, or I should say A, is the absolute value of the determinant of M. Now, in this case, okay, if the claim is true, then the inverse, let's say, for E tilde is a Borel set. Okay, this is not yet the set E. So we have another set E tilde. By the definition of the image measure, this is M sub star lambda n E tilde. And this is equal to so there must be a correction. This must be the inverse. So this is the inverse or the reciprocal of the absolute value of the determinant, lambda n E tilde. Okay, so here we applied, so this equation here is using this, and our claim that A is the reciprocal of the absolute value of the determinant. Now, taking E tilde to be Tm, E, take note that T sub m is invertible and has a continuous inverse. Therefore, this implies that the image of a Borel set is also a Borel set. Okay, so from this, it follows that so from the fact that M inverse of E tilde, well, this is nothing but Tm inverse of E tilde, this is equal to E. So from this, we have, so here, the right-hand side can be written as lambda n E. On the other hand, this would be, so the right-hand side would be lambda n T m E. And after, let's say, multiplying the determinant both sides, this equation, you can notice that. So after putting this determinant on this side, this is nothing but the equation provided here. Okay. So if once the claim has been established, this paragraph here will complete the proof. Okay, so to prove our claim, that is A is the inverse or the reciprocal of the absolute value of the determinant, we will establish this into several steps. Okay, so we will first look at the case where M, the matrix, is a special matrix. In particular, let us consider the case. This is now our second step. Suppose M is a diagonal matrix, and let us denote that by D. This means that you have a matrix where the diagonal entries is given by this vector on d1 up to dn, and the rest would be a 0. Where d1 are positive. So the entries of your diagonal matrix is positive. Okay, so from step 1, of course, with m equal to d, since d has positive diagonal entries, it is invertible. So from step 1, there exists an A positive such that d star, this image measure, is equal to A lambda n. So to compute A, first let us recall our notation Q1. So this is the unit cell. Then take note that the inverse of a diagonal matrix is also a diagonal matrix, but now the entries in the main diagonal are the reciprocals of the diagonal elements of the original matrix D. So from this, let us compute the image measure of Q1 under this matrix D. So by definition, this is lambda n d inverse Q1 but the inverse of Q1 would be a cell with the following components. So this would be the Cartesian product of these cells, dn. We know how to calculate the Lebesgue measure of this, and this is 1 over d1. So you just compute the product of the side lengths, dn, times lambda n q1. Take note that this is equal to 1. Okay, so this is in fact the reciprocal of the determinant of D. Since d sub 1s are positive, then we can write this. So you can put the absolute value since the determinant is positive. Take note that this is positive. Okay, so we know that this is equal, and we have established this equation. So comparing the coefficients, thus A must be the reciprocal of the determinant of D. And this is our claim in the case where M is a diagonal matrix having positive entries. The third step would be, what if M is an orthogonal matrix? So suppose that I have an orthogonal matrix O. That is, the transpose is equal to the inverse. Again, from step 1, we know that this image measure corresponding to this orthogonal matrix is A lambda n. Again, for some A greater than or equal to 0. So we would like to determine, again, the constant A. For an orthogonal matrix, the unit ball is left invariant. So first, let us denote B sub 1 to be the closed ball in Rn. So if X is in the closed unit ball, then if we take, let's say, the norm squared of the product of the orthogonal matrix X, O, and the vector X squared, well, this is the transpose of OX times OX, applying the properties of the transpose of a product. So we have X transpose OX. Since O is orthogonal, this is equal to the identity matrix. Hence, we end up with X transpose X, which is nothing but the norm squared of X. And therefore, taking the square root, and since X is in B1, this is less than or equal to 1. So that OX is also in B sub 1. So in other words, we have established that the image of the closed unit ball under the orthogonal matrix O is a subset of B sub 1. And taking the inverse both sides, we also have that B1 is a subset of O inverse B1. Now, observe that the inverse of an orthogonal matrix is also orthogonal. Since, well, to see this, you can check that, okay, if I take the transpose of the inverse, this is the same as the inverse of the transpose. Since O is orthogonal, the transpose of O is the inverse of O, and this is equal to this one. So therefore, the transpose of O inverse is the inverse of itself. Hence, O inverse is also orthogonal. Let us replace this. Note, okay. Therefore, if we apply or if we replace O here by O inverse, we have the following inclusion as well. And from this, we now conclude that B sub 1 is equal to O inverse B1. Where is this? According to these two inclusions. And as a result, okay, starting from this image measure of the closed unit ball, by definition, this is lambda n O inverse B1, but this is equal to what? Lambda n B1 according to this part. So we have written again we know that this image measure must be a multiple of lambda n. Comparing to this equation, we must have a equal to 1. So in the case of an orthogonal matrix, so the effect of the image measure corresponding to that matrix would be nothing. So in other words, the Lebesgue measure is preserved under orthogonal transformation. Okay, so now for the fourth step, how about scaling? So if I have a beta, which is greater than 0, then this means that I can pull out the constant in the image measure. Well, the proof is quite easy. You can, let's say, start with the left-hand side, evaluate that for a Lebesgue Borel measure, or a measurable, or a Borel set E. So with the definition implies that this is B lambda n O inverse sub E. Now, concentrating on this part, that would be, so the one inside the bracket would be O star lambda n or B. And hence, we have this equality. Now for the final step, step 5. So since M is invertible, there exists two orthogonal matrices, say O1 and O2. And okay, so let us emphasize the dimensions. So these are square matrices and a diagonal matrix D with positive diagonal entries. Such that M is the product of orthogonal O1, diagonal D, and orthogonal O2. And then the determinant of D is equal to the absolute value of the determinant of M. And this is called the singular value decomposition of your invertible matrix M. So one can factorize an invertible square matrix as a product of two orthogonal matrix and a diagonal matrix with positive entries. And the elements of, or the diagonal entries of D are called the singular values of M. So this is, in fact, a specific result in linear algebra wherein this singular value decomposition holds for not necessarily square matrices. And it also holds for matrices having complex values. However, for this specific square real valued invertible matrix, a proof was given in the course notes. So those who are interested, you can look at the proof provided in our course notes. So from this, we now prove our main theorem. So M star lambda n is O1 D O2 according to the singular value decomposition, where this product of matrices can be written as a composition of 2, or let's say of 3, matrices. And so here we applied SVD. Now applying our result on the transitivity of image measure. So we can distribute the subscript star to obtain the following equation. Considering this part, take note that the effect of an orthogonal matrix with respect to the Lebesgue measure is nothing. In other words, it is invariant under the image measure with respect to an orthogonal transformation. And this is the one provided in step 3. Now we consider this according to step 2. This is the absolute value of the determinant of D inverse. Okay, since the determinant is positive, then I can just simply write this as the determinant of D inverse lambda n. And this is our step 2 in the case of diagonal matrices. Okay, now you have a positive constant. You can pull that out in the image measure. And this is our step 4 last time. Again, invariance of the Lebesgue measure under orthogonal transformations. This is equal to lambda n. And this is again by step 3. From the singular value decomposition, the determinant of D is nothing but the inverse of the absolute value of the determinant of n. So therefore, the constant A provided in the first step must be this constant, the reciprocal of the determinant of the inverse or the determinant of the matrix M. Take note that this was our claim. Going back to that step, here is this one. And from this, we already explained how to complete the proof of the theorem. So this theorem, combined with the translation invariance of the Lebesgue-Borel measure, leads to the proof of our main theorem. So the effect of the Lebesgue measure under an affine transformation is the following. So if we want to take the Lebesgue measure of the transformed Borel set E, then this is the same as taking the Lebesgue measure of the Borel set E and then multiplied by this scaling or transformation factor. And that is the determinant of the matrix associated with the affine transformation. Again, the vector A has no effect due to the translation invariance of the Lebesgue-Borel measure. Few remarks on this theorem. This is in fact also valid even in the case where M is not invertible. So in that case, the determinant would be 0. And both sides will be now equal to 0. So if your matrix is degenerate, then your affine transformation will give you an image set that has measure 0. Moreover, this is not only true for Borel sets. One can also replace E by a Lebesgue measurable set. Recall last time that a Lebesgue measurable set is nothing but a Borel set except on a set of measure 0. So you can apply that result to extend this equation even in the case where E is a Lebesgue measurable set. In fact, that is an item in your exercise, and I'll end the lecture with that remark. See you on the next one.